Linear discrimination is a classification approach where the objective is to learn a simple, linear function separating our classes. Rather than learning the distribution of the classes, this approach focuses on learning the separation of the classes, a problem that may often be simpler to solve. We discuss in this unit about pairwise separation, about gradient descent, and about logistic discrimination. So we have discussed classification in terms of likelihood-based methods before, and in that approach the idea was that we are assuming a model for the probability distribution for each class Ci, and then we are using the Bayes rule to calculate the probability of each class given a data set. And we were looking at a discriminant function in terms of this logarithm of the probability distribution for class Ci, and we were choosing the class Ci, which was maximizing this discriminant function. Now, in the approach that we discuss in this unit, based directly on discriminants, the idea is that we would assume a model directly for the discriminant. So this is going to be a function with a number of parameters, phi I, and we will not really think about density estimation for any of the classes. We just focus on the discriminant directly. And the point here is that estimating the boundaries is sometimes enough. And we have seen an example in the previous unit in terms of decision trees. And in this unit, we take a look at linear discriminants. And the point here is that the linear discriminant is a function that has parameters wi, wi0 for each such discriminant gi. And this is a function that's linear in x. So we have this vector wi, which is multiplied with x, so that has as many components as x has, plus this free term. If you like, this can also be written in terms of this linear combination of the features, with the weights being wij and the free term being wi0. So there are some advantages in doing classification with linear discriminants as opposed to likelihood-based methods. And that is that it's a simpler method, and in particular it only takes big O of D, both in terms of space and in terms of computation time. And the other point is that to some extent you can interpret these linear discriminant methods a little bit easier. There is a way to extract knowledge, to some extent at least, because the linear discriminant, as we see in this formula, it's a weighted sum of attributes, and you can read somewhat into how large these weights are. You can think about what does it mean if a weight is positive or negative, so there is a direct correlation between that feature and the membership in that particular class, or on the contrary, there is a downward correlation between that feature and the membership in that class. You can also interpret to some extent the magnitude. Some of these features will have a bigger contribution to membership in that class than other features, depending on how large this weight is. We have also discussed that in a case where the classes are distributed with a Gaussian distribution with shared covariance matrices, these linear discriminants in fact are optimal to separate the classes. So in some cases, in fact, this is even the optimal method depending on how your data is distributed. So all of these things are points for the choosing of this linear discriminant function. Arguably, there are also weaknesses in this method, and for example, sometimes they are just too simplistic, and the classes might not be linearly separable. And this can be addressed to some extent, not always, but to some extent, it can be addressed in the following way. Maybe the classes are not linearly separable, but maybe they could be separable with some sort of quadratic function or some higher degree polynomial. And in that case, in fact, this linear discriminant method could also be used by replacing it with a so-called generalized linear model. And I want to show you that just in some details, and we are going to come back to this when we discuss pretty soon in this course about kernel methods. So here is the idea of the generalized linear model. For example, you might want to, depending on how your data is distributed, you might take a look at quadratic discriminant separating your classes. And what this means is that instead of the linear function you considered before, this time you consider a quadratic function, and that comes down to having a new factor of the form x transpose wi times x, and this wi is a d by d matrix, where d is the number of features in your data set. And then you still have the linear term as we had before, and the free term in here. So this is just an extension from the linear discriminant to quadratic discriminant. And in fact, you can also see this, and it's even by seeing it this way, you will even have an easier time generalizing this further. You can also think about this in terms of adding to your data set a few additional terms, a few higher order product terms. So in other words, to the features you already have, say x1, x2, all the way to xd, you can also add, so this is an example where we only have two features, you can also add x1 squared, x2 squared, and x1, x2. So all the terms of, all the second degree terms. And you can also extend this to third degree terms, and you write here all the combinations of degree 3 and so on. And once you do this, in fact, you can reduce your problem to the linear discriminant, because the quadratic discriminant we discuss in here, in fact, is a linear discriminant in terms of these extended features we have in here. So that's also a way of obtaining a nonlinear separation using a linear discriminant by adding these extra features. So in general, the idea here is that you might get an extended discriminator by mapping from x to z using some sort of nonlinear basis functions. And then we are using a linear discriminant in this z space. So your discriminant is going to be a linear one, but it's linear not in the original features, but in these transformed features. And the transformation could be something like this, but it could also be much more complex than that. You could have a transformation of your features in terms of, say, sine functions or cosine functions or exponentials or whatever you think you might need depending on your data distribution.